Did you know that invisible chemical links are the key to understanding why your electronic devices fail? Discover the mystery behind the stability of transistors and how a single electron can trigger their deterioration. This invisible wear represents one of the great challenges of today's engineering. It limits the useful life of technologies we use on a daily basis. Therefore, understanding the mechanisms behind this deterioration is crucial. A recent study focuses on the links between silicon and hydrogen, essential for stabilizing defects in chips. This paper proposes a theoretical framework that describes how energy electrons interact with these bonds. For years, it had been difficult to explain this phenomenon accurately. The current electronic devices are based on semiconductor materials, the silicon being the most important. In its structure, natural defects appear that can alter the electrical behavior. To neutralize these defects, hydrogen is introduced, a process known as passivation. However, this balance is not permanent. The functioning of the device involves the passage of electrons, which can interact with the bonds. The rupture of these bonds is related to phenomena that affect the reliability of the transistors. Although electrons were known to break bonds, the exact mechanism was not clear. Previous experiments showed hard to conciliate results. There was a missing model that would unify all these observations. One of the major obstacles has been the theoretical framework. Usual methods in material physics separate the movement of electrons and atomic nuclei. However, in this case, that separation does not work well, since the rupture of the bond depends on the direct interaction between the two. The study introduces a non-diabatic approach, where electrons and nuclei influence each other in real time. This change of perspective allows connecting concepts of chemistry, physics of the solid state, and quantum mechanics in the same framework. The study identifies specific electronic states associated with silicon-hydrogen bonding. Link dissociation can occur when electrons temporarily occupy the anti-linking states. This detail changes the classical interpretation of the process. Once the electron occupies that state, hydrogen begins to move in a repulsive energy landscape. However, the result is not completely determined. This process is probabilistic and depends on how long the electron remains in that state. The model not only explains concrete observations, but also connects different types of experiments. This suggests that the mechanism identified is general and not exclusive to an experimental context. In addition, it can be applied to other materials and processes where energetic electrons intervene.